In the next few lecture segments, we'll review Java's object-oriented features, including classes, objects, static and non-static methods and members, constructors, inheritance, method redefinition, polymorphism, static and non-static inner classes, and more. Now, you're expected to have already worked with classes and objects in Java, see the Java Review module if not, and with inheritance in Java or some other language, though it's okay if you're a bit rusty. We won't talk about these topics at an introductory level, but we will review all the basics. Now, for these and later topics, we're going to use a virtual world, dubbed Code Worlds, as our model. Think of a simplified Minecraft, perhaps, or a more elaborate version of the AP Computer Science Grid World. We'll start with simple example classes supporting Code Worlds, and then improve and expand on them, learning about object-oriented design and design patterns as we do. So let's start with a class that will be ubiquitous in Code Worlds, and that is vector. Any simulated world requires a vector class of some sort to represent locations of objects in the world and their velocities and possibly even their accelerations. Code Worlds, at least at this point in our discussion, is two-dimensional for simplicity, so our vector class has just two member data x and y. There'll be more on k epsilon in a bit. Now, these two member data might represent a position, a velocity, or any two-dimensional value that we like. And they're declared protected, which means they're accessible within vector and in any class derived from vector, and also per Java's odd design, it means they're accessible to any other class within the same package, com.cstaley JavaOO basics. We'll ignore that fact and assume they're only accessible to vector and derived classes. Now, the vector constructor does what constructors do in any object-oriented language. It initializes the content of an object. You can ignore the comment in the parameter list for the moment. We'll return to it shortly. Now, a statement like this one down in testvector.java, which I have at the bottom of our slide here, v1 equals new vector 1.0 or 1.0 That statement allocates memory, of course, for a new vector object and calls the constructor to initialize the object, passing any constructor parameters in parentheses after the type name in the new statement. An important point, by the way, often misunderstood, is that the constructor does not allocate space for the vector object. It only initializes it. The space is allocated by new before calling the constructor. And back up in the constructor body, note the use of this.x and this.y. Because our parameters have the same name as the member data, that's a somewhat common style pattern in constructors, we're going to use this.x to specify that we mean the member datum x of the object being initialized, which is this. Now let's take a look at the getters and setters for a moment. At least for any complex class, proper design hides the member data via protected or private status and permits access only via methods to retrieve and possibly set the members. The universal style in Java is to name these methods get such and such or set such and such with such and such, the name of the member datum, thus our get x and get y. The set methods are omitted if you want the member datum to be read only from the outside the class and not written, as we do here in vector. And note that once again I inserted a comment, vector this, with into the header for getX, and explicitly and needlessly in this case I added this dot in the return statement. It's time to talk about why I did that. Now, even programmers familiar with object-oriented languages sometimes do not completely understand the mechanism by which method calls are made. And this mechanism is universal to all object-oriented languages, so it's worth going over. Consider in the notes here this method in any OO language. List.add, I'll put it up here as well, list.add 42 we'll say. So it's expected to add 42 to the list object, of course, but here's a question for you. How many parameters does that add function truly have? And the word truly should signal that the answer is not the obvious response of 1. Returning from a pause, if you can confidently say 2 parameters, of course, because the first one is hidden and it's a reference to object list, in that case you can skip this next section or at least read it very lightly. Otherwise, listen and read on here. The abstract object-oriented model of an object is that it's a bundle of data and methods, like this diagram here that I've labeled the illusion. The abstract model says that each object has its own copy of the methods. This ensures that the methods of object A work on object A, and those of object B work on object B. Now, it's a useful abstraction, but it's a lie. Copying the same method code over and over again in possibly thousands of different objects would be senselessly inefficient. No object-oriented language does that. Instead, in every object-oriented language, there is only one copy of any given member function, no matter how many objects there are that include that member function. Let's draw the reality down here, showing how things work under the hood. In this diagram, vectors v1 and v2 have their own copies of the data, but they include no methods. The methods are drawn separately, and there's only one copy of them shared by the objects. So this invites the question, when I call v1, say, .getX versus v2.getX, how does the one and only getX function know which vector it's supposed to use? Whose x value does it return? The answer, again in every language, is that getX is passed a hidden extra parameter, telling it what object it's supposed to operate on, what object it belongs to for the current call. On each call, this parameter may point to a different object. And so, in effect, getX busily makes believe it's a distinct copy for each of the different objects. But that's an illusion. The function is really being told which object to belong to on each call. Now, this extra parameter is not visible in the parameter list, but it's there, silently added by the compiler. I've heard one colleague call this sneaking in the object, and that's a good description. The hidden parameter is called this in almost every object-oriented language, including Java, and it's always a pointer, or as in Java, a reference. That's why you can use this in member functions. It's not a magic keyword, it's just the name of a parameter you have but didn't declare. Now, the target of this needs a name also. There's no field universal name, but in these lectures we'll call it the context object. That's one of the most important terms of the class, so be sure you understand what we mean by it. The context object is the object pointed to by this, the object upon which the method is working in the current call. For getX and a few other methods, I've explicitly shown the this parameter in comments. Here and here, for instance. Where I have not shown it, you should mentally envision it anyway, except for static methods, which we'll discuss momentarily. Now, also in the getX method, I've explicitly used this.x instead of x. You're always allowed to do this, but it's not needed except in cases where you must distinguish between a member datum and some other variable, as in the constructor we just discussed. If you use a member datum by name alone, then the compiler automatically adds the this. So return y gets silently revised to return this.y. Of minor note, by the way, is the fact that there is one popular language where you must use this dot to reference a member datum, and that's JavaScript. A JS interpreter won't add the this dot automatically. Now, how does the interpreter or compiler determine what to pass as this? By the object you use to make the call. If you say, for instance, v1 dot get x, then v1 is passed as this. But if you say v2 dot get x, then of course v2 is passed. And in the case of constructors, which also have a hidden this parameter, as the comment in the vector constructor showed, the just allocated but uninitialized object is passed. So, summarizing, for non-static methods, the compiler silently adds a this parameter. And then point 2, for uses of member data within the method, the compiler silently adds this dot, if you don't already. And when calling the method, the compiler silently passes the object used for the call, or the just allocated object in a new call, as the target of this. And so the illusion is complete. And you can code as if the function is inside the object and as if each object has its own personal copy of the function. But being aware of the reality helps a great deal in understanding object-oriented language behavior. Here's question 2 for you. If method A calls method B, as in the notes here, where I have a class of A and B, then what context object does the call of B get? There's no explicit object used to call it. Show how the compiler would effectively rewrite that call of B with the extra hidden parameter. Returning from a pause, B would have to get the same context object as A. The call would be rewritten as B parenthesis this, meaning that would effectively pass A's context object along to B. Okay, in the next segment, we'll look at the remaining methods of vector.